The focus of this video will be on coordinate transformation and how to compute the stresses on body parts with respect to a rotated coordinate system.
First of all, what is the coordinate transformation good for and when do you use it? Let's suppose you have a plain piece of metal or a plain piece of wood that is subjected to various stresses, such as normal stress in x direction, normal stress in y direction, as well as shear stresses. The magnitudes of shear stresses are identical as per the equilibrium conditions for force and moments. And now we want to make a cut through that body at a specific angle to the x-axis. In our example, the cutting angle is 70 degrees to the x-axis. That leaves us with two separated body parts, and now we want to glue or to weld these parts together. And our goal is to calculate the stresses that occur with respect to the rotated coordinate system. So if you make a cut through the body, it is common to lay the y-axis, the new y-axis of the rotated coordinate system, which I have labeled as y star, parallel to the cutting area, while the new x-axis, which is labeled as x star, runs perpendicularly to the cutting area. And in our situation, if we glue or weld these parts together and we apply the same stresses as shown here, the stresses with respect to the coordinates, to the rotated coordinate system, will turn out to be as indicated here. And we want to be able to compute the magnitudes of normal stress and shear stress with respect to the rotated coordinate system. And to do that, we're gonna be using this set of formulas. So this one is for the normal stress in x direction of the rotated coordinate system. This one is for the y direction, and the formula for shear stresses in the rotated coordinate system is this. And as I said, it is still true that the magnitudes of shear stresses are identical. So before we start, let me give a remark at this point, which is important. The example demands that we perform a cut at an angle of 70 degrees to the x-axis. The variable alpha in this formula does not refer to the cutting angle per se, so keep that in mind. The angle alpha actually refers to the angle by which the coordinate system rotates. So as you can see, if we lay the new y-axis parallel to the cutting area, the rotation angle of the new coordinate system compared to the old one will be 20 degrees clockwise. And know that if you have a rotation of your coordinate system or rotation of any other object that is clockwise, the associated angle is negative. And this is where I have to make a correction here. So you see the angle was positive, but it should be negative because the rotation is clockwise. And in mathematics, rotations that are clockwise are considered negative, while counterclockwise rotations are considered positive. So if the cutting angle is 70 degrees, as I said, the value of alpha is 20 degrees, or in our case minus 20 degrees because of the clockwise rotation. And that's because the right angle has 90 degrees, so we have cut off 70 degrees, and that leaves us with 20 degrees. And let's start calculating the values for the normal stresses and the shear stress in the rotated coordinate system. The values of stress in the old coordinate system are given. We have sigma x, which is minus 20 megapascal, and as far as the algebraic sign, let me tell you one more piece of information. The arrows that you see here are the assumed stresses. When I say assumed, I mean assumed from a mathematical standpoint. That means that if the stress values are positive, the actual stresses act in the directions as shown. If the stress values are negative, the actual stresses act in the opposed direction. So for sigma x, the normal stress in x direction, the actual stress would act in the opposing direction. That means to the left. And that would leave us with compressive stress, because we would have a stress to the left on this side and then a stress acting to the right on the left side. That would generate a compressive stress. And for sigma y, the normal stress in y direction, the value of 60 megapascal is positive, and that means that the actual direction is in line with the mathematically assumed direction. For the shear stresses, you have to reverse the direction compared to the directions labeled on the sketch. So let's grab the first formula for sigma x star. That's the stress magnitude in the x direction of the new coordinate system. And that is equal to 1/2. Sigma x is minus 20 megapascal. So I should insert the negative value right away. Plus sigma y, so plus 60 megapascal. Plus 1/2. Sigma x, again, is minus 20. Minus sigma y means minus 60. Times cosine of 2 times alpha. Alpha is minus 20 degrees. So 2 times alpha would be minus 40 degrees. Plus tau xy, which is minus 30 megapascal. So I'm gonna put a bracket and write down minus 30 megapascal. Times the sine of minus 40 degrees. And the value of sigma x star is equivalent to 8.64 megapascal. So sigma x star, that's the normal force that is labeled here. So the normal stress in the direction perpendicular to the cutting area is 8.64 megapascal. And keep in mind that this normal force is made up of the normal stress is made up of various stresses that you can see on this sketch. Okay, as far as sigma y and tau, I'm not gonna plug in the numbers to save time. I will write down the results right away. So sigma y star, and again, sorry if I sometimes confuse force and stress. That's quite easy to confuse. but you gotta be precise. So sigma y star is equal to positive 31.36 megapascal. And that's the stress that acts in this direction, parallel to the cutting area. And finally, we need to determine tau, x star, y star. That's equal, so if you plug the values into this formula, you're gonna get minus 48.69 megapascal. We have computed the values for normal stress and shear stress in the rotated coordinate system, and now you might be wondering, what do we make of these stress values? Let me tell you. If you have your two separated body parts that are held together by glue, weld, or screws, you know that the normal stress in x star direction, meaning in the direction perpendicular to the cutting area, must be 8.64 megapascal. The normal stress in y star direction is 31.36 megapascal, and the shear stress that the glue or the screws must withstand is 48.69 megapascal. Since the value for shear stress is negative, that means that the actual shear stress does not act in the direction as indicated, it acts in the opposed direction. That means to the southwest. And just for your information, let me add that tau, x star, y star, is equivalent to tau, y star, x star. That would be the shear stress, which I have not indicated here. That would be the shear stress acting perpendicularly to the cutting area.
So far, so good. I hope that you understand how to perform the coordinate transformation and that you understand its purpose.